Hello, and welcome to the lecture for Chapter 14 from Conceptual Physical Science. In this chapter, we're going to formally introduce chemistry. We've been leading up to chemistry with chapters 12 and 13. This is the first one that, of course, has chemistry in its name. So let's go ahead and take a look at what we're going to be talking about in this chapter, okay? And, of course, in this lecture. So here we're just going to introduce what chemistry is, how it's the central science, which is to say it acts like a bridge between other sciences, all right, other fields of scientific research. Then we'll talk about the submicroscopic world, a term that we've been using quite a bit, but I'll kind of remind you what that term means. Then we'll talk about the physical and chemical properties, all right? Kind of what's the difference between the two. So what's a physical property versus what's a chemical property? And that actually is an important distinguishing characteristic that we need to make sure we understand from this chapter. It's one of those key takeaways, okay? Then we'll talk about physical and chemical changes, which very much follows from the definitions of what the properties are. Then we'll talk about elements of a compound, which just adds to what we already introduced in the periodic table 2 lectures ago, so 2 chapters ago. That would be back in chapter 12 when we first introduced the periodic table. Make sure you watch the lecture for chapter 12 first so you see what the periodic table is all about. And then we'll finally talk about naming compounds, which is just an idea about when you see all those chemical equations, how do we make sense of them? We sort of have to learn a small language in terms of naming those compounds. And we want to make sure that we're familiar with that and know how to do it. It's a good skill. Okay, so let's move on. And by the way, this chapter and this lecture are pretty light on the more difficult ideas, certainly light on the mathematical side. It very much is a introductory chapter in a sense, because we're going to be talking about chemistry for the next few chapters, okay? And I guess we can really say we've left physics, the field of research known as physics, behind us and have firmly moved into chemistry, okay? The so-called central science. So chemistry is the study of matter and the transformations it can undergo, okay? Now, it isn't interested in the nucleus because certainly matter and changing inside the nucleus, matter changing into energy, transmutation of elements, those are all nuclear processes. Those are interestingly not considered chemistry. Those are all considered within physics, okay? But on the macroscopic scale, mixing things together, making explosions, all those sorts of ideas. What you think of chemical compounds do you find under your sink in your home? That is definitely firmly chemistry, and that is all transformations of matter, but at the molecular scale. So mixing different atoms together. Okay. And by the way, the idea of mixing atoms together, we're certainly going to talk a lot more about in future chapters. Okay. So here we have looking at a diamond, considering the chemistry that goes into how do diamonds form? How do you mix diamonds with other metals? Okay. All right. Here we have someone on the moon where there is very little atmosphere. So chemically speaking, the area above this astronaut would not have too much of interest, but certainly the chemistry of the sand, the regolith as it's known on the moon, has very different compositions than say the chemical dirt that you would find on Earth, okay, or the chemical composition of dirt you would find on Earth. All right, so chemistry comes up everywhere. All right, certainly a chemist would be a part of a scientific team if we go into space and so on. Okay. And here's this idea of chemistry acting like a bridge. So physics is this fundamental science. We've seen what physics is all about. It's understanding the laws of motion, the laws of conservation, and also studying the very, very small and the very fast, these big fundamental questions. But then chemistry is going to then help bring physics into application of molecular compounds, which will help us understand biology, right? Biology here on Earth, perhaps in the future, biology on other planets. It helps us understand the composition of stars, the composition of atmospheres of planets, certainly the composition of the interstellar medium between the stars, which would all fall into the category of astronomy, those nebula where stars are born. And we'll talk about that more. And then chemistry is certainly very important for earth science in terms of understanding the chemical composition of rocks, the chemical composition of lava, what are the chemicals that exist inside of our planet, why are they there, what should we expect, how do they behave a certain way, and indeed we'll touch on that in our chapters on earth science after we finish up this unit on chemistry. Okay, so very much a bridge of a science and centrally located because it can be applied and help one way or another. Okay. It is a material science, and this is probably the way I think of it the most. Chemistry is all about understanding materials. whether that's making rubber and different types of rubber, or whether that's mixing a new cleaning agent, that's at the material level. And that is not a submicroscopic phenomenon, but we need to understand what's happening at the submicroscopic level to make sure we make those macroscopic or everyday items correctly. Okay, so a chemical company is interested in creating materials. All right. So most of the material items in our modern house are shaped by some human-devised chemical process. All right, so we have over the last few centuries come up as a civilization with many, many clever chemical processes. Okay, so here is a typical human kitchen. All right, so let's think about all the chemical processes that were necessary to build something like this. All right. Well, we had to have a transparent matrix of processed silicon dioxide to make those windows there, all right? We have to have chemically disinfected drinking water, right? Our water is just not, natural water out of the ground. We disinfect it with particular chemical solutions that we found work well and aren't harmful. All right, we have a caffeine solution, right? That's a chemical process to extract the caffeine. It's a chemical process to get the amounts of caffeine. And of course, if you look at the ingredients on processed coffee, there's more than just coffee beans in there. All right, then we have thermoset polymer, which is the plastic top here, the plastic countertop. All right, so a polymer just being derived a particular type of plastic. Now we think of plastics as coming from oil out of the ground, which is basically a type of fossil or highly pressurized fossil. But we can also make plastics from other sources like fungi and plants. But point being is that we're interested in these chemical chains, and polymer is very much a term you should think of as a chain of chemicals that has particular characteristics. Well, moving right on, we have prescription medicine stored in the refrigerator. We have chlorofluorocarbon-free refrigerator fluids, right? So that's your refrigerator fluid. Chlorofluorocarbon-free is important for not harming the environment excessively. That was one of the chemicals that was removed as we tried to assess climate change. We have electrical energy from a fossil fuel or nuclear power plant in the light, which I would argue is more of a physical phenomenon. But then we certainly have a metal alloy in our pan there, or our cooking pot, because in this case, this is not just just a chunk of metal we dig out of the ground. We have done a lot to process that metal and think about how we can combine different elements of metal to make alloys, because an alloy is a mix of different metals. We have roasting carbohydrates, fats, proteins, and vitamins inside of the oven. All right. So certainly dealing with food science is very much a chemical study, right? So food science and chemistry, you can really think of food science as being a subcategory of chemistry, very much so. We have natural gas laced with odoriferous sulfur compounds, because otherwise the natural gas would have no smell to it, which is dangerous. So we actually mix a compound in there so we can smell it. That way you know if the gas is leaking. And then we have fertilizer grown vegetables, because it's so important what chemicals we put into our farm soil in order to get our vegetables to grow well. And of course, we're ignoring the fact that the pesticides and the fungicides are also chemically derived compounds or materials that are so important for growing crops at the scale that we need to feed almost 8 billion people in the world. Okay? So chemistry is so important for really our sustained success as a species and civilization. So more than 70% of all legislation placed before the Congress of the United States addresses science-related questions and issues, okay? It's just, of course, right? Science is truly everywhere. You can't just ignore it. And talking about chemistry, I think, is really bringing that to the forefront here in this chapter. Okay, so a situation to ponder, and while we're introducing chemistry and sort of selling its importance, I hope that's what it seems like here, is that collagen cross-link inhibitors that significantly reverse various aspects of aging have recently been discovered. Okay, so is chemistry going to lead to longer lives? Well, quite possibly. All right. So clinically tested to be safe and effective collagen cross-link inhibitors should be available to the general public, and I just want you to think about this, available only to those 21 and older, available only by prescription, prohibited because of their abuse potential, or prohibited because of growing old should be natural, right? Should we not interfere with it? Okay? Well, it's up to you to decide, right? You have to know more about it, because if you just know it's this collagen cross-linked inhibitor, well, what does that really mean, right? So you have to have some scientific literacy to make informed decisions. Okay, so a single grain of sand contains about 125 million trillion atoms. And I've talked a lot about the number of atoms in small samples of material. We've talked about how it's often something on the order of 10 to the 24 atoms is, kind of a typical number for larger samples. In this case, if we have a million, which is 10 to the 6, that's 6 zeros, and we have a trillion, which is 10 to the 12, then you see we're dealing with 10 to the 18, and over here we have 10 to the 2, because 100 is 10 raised to the second power. So if we add together the exponents, 2 plus 6 plus 12, we see we get up to 20, or 10 to the 20 atoms. But of course, that's for a very small sample because a grain of sand is very small, okay? All right, so how much is 125 million trillion? Well, you saw it in terms of just the exponents, 125 times 10 to the 6 times 10 to the 12, okay? So roughly, but that's hard to visualize, right? And maybe, just thinking about the exponents isn't terribly informative for you. I think over time, it certainly is a good way to think about numbers. I think about numbers that way, and I count the zeros. But some analogy, some way to actually kind of conceptualize or visualize a number that large is, of course, helpful, right? For anyone, including myself. So roughly 250,000 dunes of this size contain about 125 million trillion grains of sand, okay? So this is helpful because we're thinking about, well, if there's that many atoms in one grain of sand, how many grains of sand would be also that big number, that number of 125 million trillion? Well, let's see, right? It's 250,000 dunes. So big, giant dunes like that, right? So enough dunes to cover a very large region of a continent, for example, right? 250,000 is significant, okay? A country-sized expanse of sand, okay? Yet that's how many atoms there are in a single grain of sand. It really gives you an idea of how small atoms are, okay? Atoms, in terms of their actual size, are on the order of 10 to the negative 10 meters. That's kind of like their size across. Now, obviously, we already talked about how atoms vary in size due to the electron distribution, and we talked about how the actual size of the nucleus is significantly smaller than the atom as a whole. But if we're just kind of taking a rough average here of atomic size, 10 to the negative 10 is a helpful number to remember, okay? So essentially, that's how small they are, right? And that is very, very small, right? So in comparison, if you think of a small bacteria, a bacteria in size, put it up here, bacteria, is about 10 to the negative 6 meters. It's about 1 micron in size on the smaller end of bacteria, okay? So we see then that an atom is about 10,000 times smaller than a bacteria. But of course that makes sense because bacteria are living organisms composed of organelles, biologically speaking, something we won't talk about because we're not covering biology here, only the physical sciences. But the bacteria is formed of all those molecules, biological molecules. Each of those molecules is then itself formed of atoms. So it makes sense that the bacteria, even being a very simple, very small organism, is still 10,000 times larger than the individual building block of matter, okay? Right? And 10,000 times in terms of a size difference is pretty significant, okay? So, are atoms made of molecules or are molecules made of atoms? I bet you know it, but this is important that we make sure to establish here, okay? Well, all right, which is it? Well, let's think, right? Here we have an oxygen atom within a water molecule, see? And that water molecule also has 2 hydrogen atoms. So the atoms make up the molecule. Atoms aren't included in molecules. Molecules are bigger than atoms, okay? In fact, a single atom we would never call a molecule, but sometimes we could just have 2 atoms together, and then that would be at that point, even just with 2, is then a molecule. This would be a diatomic, di meaning 2, it's a prefix for 2, diatomic molecule. That basically the smallest molecule you can come up with. For example, hydrogen forms a diatomic molecule, H2. Of course, when there's an oxygen around, it wants to bond with the oxygen. And we'll talk about the desire of molecules to bond, desire in quotes, or more the propensity for molecules to bond later in later chapters. But point being, you can have diatomic hydrogen, but you can also have oxygen, where there's 2 hydrogen mixed with an oxygen, or I should say you have a water molecule, H2O, okay? So a physical property describes the look or feel of a substance. So what we're doing here is we're going to establish the difference between physical and chemical properties. I talked about this in the table of contents to start off the lecture. That we're going to definitely establish the terms here, okay? So again, a physical property describes the look or feel of a substance, right? For example, opacity, color, the phase, right, whether it's a solid or a liquid or a gas, right? Its density, those are all examples of physical properties. And we can compare between gold, diamond, water. Water is in a phase of a liquid at 25 degrees Celsius, whereas of course, diamonds and gold are in a solid phase at that same temperature, okay? But then opacity is about how much light can shine through. That's obviously related to the ability of the atoms to transmit photons of the visible section of the electromagnetic spectrum, ideas reviewed in previous chapters, okay? And so we can say that gold is opaque. It's not transparent to visible light, all right? It is certainly transparent to some type of electromagnetic radiation, but not visible light, all right? But diamonds are transparent, as is water, okay? We can then talk about the color and so on, all examples of physical properties. A chemical property, on the other hand, describes the tendency of a substance to transform into a new substance. And we are not talking about transmutation, okay? Not transmutation, because transmutation involved element to a new element, okay? It involved a change at the nuclear level, but substance is not an element. A substance is a mix of elements, okay? All right, so important distinguishing difference here between transmutation and chemical process, okay? So it is a chemical property of iron to transform into rust. The molecules, a new molecule is formed, I should say, when the iron combines with oxygen, okay? So that's a molecular process, which is a chemical process. So physical changes is a change in the physical property of a substance. So transmutation, the change of the nucleus, would be a physical process. But there's less dramatic examples of physical processes as well. Of course, a phase change is an example of a physical process, changing from one phase to another, okay? So boiling, melting, great examples of physical changes, okay? A chemical change is the transformation of one or more substance into another. All right, so methane reacts with oxygen to form carbon dioxide. All right, so you see that? So you have methane, a chemical compound, a molecule, mixing with a different atom in this case, but still, we started with at least one molecule, and then we're going to form a new molecule. So these are molecular processes. All right, baking soda reacts with vinegar. All right, both molecules to form carbon dioxide and water, forming new molecules. So those are all chemical changes, all right? And copper reacts with carbon dioxide and water to form the greenish blue substance called patina, all right? Pretty cool. So a substance is identified not only by the kinds of atoms it contains, but also by how those atoms are connected to one another. And that is a molecule, all right? So it's a molecule, in other words, is bigger than the sum of its parts. Just knowing the atoms in a molecule aren't enough. You need to know how they're connected, okay? And there's so much in that statement. It's so much of the next chapters are going to be all about understanding how atoms are connected on a basic level, right? Appropriate to this class, of course, but then helping us then make sense of those different ways that atoms can connect and giving us some intuition and some important facts about molecules. All right, so during a chemical change, a new substance is formed as atoms rearrange themselves into new configurations, okay? And they bond together, all right? So let's look at an example here. We have oxygen. Oxygen, like other simple atoms or light atoms in the periodic table, so atoms with a low number in terms of their atomic number, well, they tend to form these diatomic gases, especially if they're in a gaseous state. So this is O2. I already mentioned that hydrogen tends to form diatomic hydrogen, which is H2. Well, here we have O2. So we have two oxygens bond together. And if there's a methane around, then what's going to happen is the diatomic oxygen is going to break apart the methane, right? Because there's going to be an attraction that's going to pull off the molecules, the hydrogen molecules, which are these ones here, from the methane, leaving them behind, all right? So then we have a state where everything is individual, all right? Because the bond that held the diatomic oxygen together isn't strong enough to overcome this attractive force between what? Well, between the hydrogen and the oxygen, because the hydrogens, two of them, and oxygen have a stronger attractive force than what held the methane together. So in other words, the oxygen pulled the methane apart, formed water, as we can see, and then the leftover carbon, which was the black atom shown in the methane molecule, that leftover carbon then will bond with available hydrogens. Okay, it won't form a new methane because all the or leftover oxygens, excuse me, not hydrogens, but because all the hydrogens are going to want to bond to oxygens. So only free oxygens will bond to the carbon. So in other words, methane and oxygen, when exposed to each other, form carbon dioxide and water. Okay, that's a chemical process, right? Why does it tend to do that? Well, there's certain energies that are favorable in that final state. In other words, there are forces that pull things apart and forces that pull together the new molecules. So the physics side is still there. Energy, right? What direction are we going in energy? We're transforming energy from one form to another. We're decreasing the amount of potential energy in the chemical bonds, and forces of attraction, forces of repulsion. All right. So the transformation of oxygen, O2, into ozone, which is O3, so like triatomic oxygen, is an example of what? Is it a physical change? Is it a chemical change? Or is it both physical and chemical? Or is it neither, right? Is this a trick question? So what do you think? O2 into ozone, is that a physical, chemical change, or something else? It's, of course, a chemical change. A perfect example of a chemical change. Taking an existing molecule and making a new molecule. All right? So a physical change imposes a new set of conditions on the same material, right? And when we say material, this obviously a gas is also included in our broad category of what a material is, okay? So a chemical change forms a new material with its own unique set of physical properties. So that's interesting, right? Because if you think about diatomic oxygen, O2, compared to ozone, well, they have different boiling points. They have different opacities for different wavelengths of light. So those are all physical properties that now the molecule is going to exhibit, right? So it's so interesting that the chemical change results in different physical characteristics, okay? So both physical and chemical changes result in a change in physical appearance, all right? So you can get a change in physical appearance through boiling, an entirely physical process, but you can get a change in physical appearance also from a chemical process. Get it? All right. So melting a piece of solid gold would be what? Would that be a physical change, a chemical change, both, or neither? I bet you know it. That one's physical. Any phase change like that is purely physical because you didn't change the gold, it remained gold. Okay? All right. Tarnishing a piece of silver would be physical, chemical, both, or neither. Tarnishing. What do you think? What does that sound like? That's chemical, all right? So tarnish transforms pure silver, which is elemental silver from the periodic table, to silver sulfide, which is a molecule represented in molecular language as Ag2S. And we'll talk more about reading compounds at the end of this lecture. Okay, so to review, an element is a material made of only one kind of atom. Pure gold is an example, as it is made of only gold atoms. Okay, so that's an elemental material. Indeed, we defined that in a previous chapter, but it's good to review it here. An atom, the fundamental unit of an element. You should know that again from a previous chapter and lecture. So the term element is used when referring to macroscopic quantities. The term atom is used when discussing the submicroscopic, okay? On that scale of 10 to the negative 10 meters, right? The scale of atoms, right? And by scale, I mean size. So the elemental formula used to show the proportion by which atoms combine to form an element, okay? Because we saw with water, for example, there's 2 oxygens. Well, yeah, no, there's 2 hydrogens per 1 oxygen. That's what we mean by the proportion, right? That would be a 2 to 1, 2 hydrogens per every 1 oxygen. Get it? Okay. So that's molecules tend to form in certain ways. Again, we'll talk about why they tend to form that way in future chapters. But oxygen, right, has a formula of O2 because a single oxygen atom on its own doesn't like to be on its own. There is a force, there is a energy propensity for it to bond with another oxygen. Okay, so it forms O2. Ozone, we already talked about, is O3. Sulfur, interestingly, tend to form in sulfur gas as S8. All right, and then gold is just going to be a single gold atom. All right. So a compound is a substance consisting of atoms of different elements, okay? So for example, if you have a sodium atom and a chlorine atom, that forms a compound, all right? Or sodium chloride, which is called, that's what that compound is called, is represented by Na, the letter from the periodic table for sodium, and chlorine, Cl, again, just the shorthand, the acronym for chlorine from the periodic table. And don't memorize these, just look them up when needed, right? Likewise, we can have ammonia, which is NH3, in other words, 3 hydrogen atoms formed with 1 nitrogen atom, making a compound or a molecule, all right? A molecule. So think of a compound as being many molecules, okay? It is the substance on the macroscopic level, but if we were to take a compound of ammonia and just extract a single molecule, then that would be the building block of that compound, the smallest piece, all right? So compounds have properties uniquely different from the elements from which they are made, okay? They're, again, different boiling points, different opacity, different densities, right? These are all different conductivities. All these properties that are so important, right? How do they conduct heat? How do they conduct electricity? That's going to change when you go from one compound to another. Okay, so sodium metal, all right, because sodium does form a metal when it's in its pure state. So this is just pure Na. And chlorine gas, because at room temperature, chlorine is going to be a gas, all right, Cl. Together, they react to make sodium chloride, something totally different, okay? And if you look at the phase of the sodium chloride, it's going to be in a solid, in a chunky solid, right? Because what is it? It's salt, all right? The sodium on its own is a metal that is not exactly harmful, but also it is very reactant to water. So if you expose water to it, it's going to burst into flame. It's going to have a very high energy process, all right? And so it's dangerous in that sense. Chlorine, pure chlorine gas, is incredibly harmful. But if you mix the two together, then they form absolutely ingestible, healthy salt. Right? So a good example of, on the biological side, maybe a side we can easily relate to, how mixing things together are going to behave very differently in our bodies, in our biological systems. So chemical formulas, which we started to see, are used to show the proportion by which elements combine to form a compound. Okay, so chemical formulas, for example, sodium chloride. We saw this one, it's NaCl because it's 1 sodium per 1 chloride, all right? It's 1 to 1. On the other hand, ammonia is always 3 hydrogens for every 1 nitrogen. Likewise, water is 2 hydrogens for every 1 oxygen, okay? So what are the guidelines for naming compounds? This part's kind of interesting. I want to make sure we have kind of this established out of the way. I think this is kind of fun, all right? So we start with the element furthest to the left in the periodic table, right? That's the one that's going to come first. And you probably wondered, you know, if you were an astute viewer here, you probably wondered, why did hydrogen come second for ammonia, but hydrogen came first for water, right? Is that an arbitrary choice? No, it's following the guideline, right? So start with the element furthest to the left in the periodic table, right? So that's going to be in the group that has the lowest number, okay? Because remember, groups are the columns, periods are the rows. Okay, so for the element to the right, add the suffix "ide", okay? Right, and we'll show examples of this. Example, NaCl, so that's 1 sodium and 1 chlorine atom, forms, right? Well, sodium and chlorine. And a minute ago, I called the individual chlorine atom, I called it chloride. That was just a slip of the tongue. It's only chloride once it forms the compound or once it forms the molecule, but you'll see that in just a second. So here we have sodium. Okay, sodium is going to come first because it's in the lower group. It's in group 1, all right? Chlorine is going to come later because it's in a higher group, all right? And so that's why it's in that order. And then the name, we see we're going to change chlorine to chloride because simply it is the higher group and it comes second, okay? So it becomes chloride only because it's second. So then the name of the compound or the name of an individual atom of 1 sodium and 1 chlorine is sodium chloride, NaCl, okay? So good example there. So with different possible combination of elements, we use prefixes to remove the ambiguity, okay? So what do you mean by that? Well, we have mono, which is just a single one. We have di, which is 2, like diatomic hydrogen. We have tri, which is 3, and tetra, which is 4, okay? All right, so that's gonna clear up when there's multiple of an individual atom in our compound, okay? Example, CO and CO2, because otherwise they would, you know, if there was no way to distinguish between 1 versus 2 oxygen, these would be said the same, but obviously they're not, all right? The first one is carbon monoxide, right? And otherwise it would just be carbon oxide, but since there are other cases of this atom, where multiple oxygens can form with a single carbon. That's why we call it monoxide. So it's sort of this naming convention here. The mon for one is, or the mono for one. In this case, it's monooxide, which is why it says monoxide. Well, it's just in preparation to the knowledge that there are other combinations. Okay. Again, we don't. I guess the best way to say that is, notice we did not call it sodium monochloride. Okay. We could, but that would be unnecessary because there's no such thing as sodium dichloride. Okay. But since there is such a thing as carbon dioxide, then, well, there we go. We've got carbon monoxide. Okay. All right. And di just meaning two. Two versus one. And one referring to the number of the atom that follows the prefix. Okay. So another example, dihydrogen, because the hydrogen comes first because it's further to the left on the periodic table. We're reading from left to right. So dihydrogen and then monoxide. On the other hand, we could have dihydrogen dioxide, right? Pretty cool. So would you drink this? Would you drink dihydrogen monoxide? Sounds kind of dangerous, right? But of course you would. It's just H2O, which is just water, all right? But as far as dihydrogen dioxide, you probably wouldn't want to drink that because it's hydrogen peroxide, but you certainly would want to pour it on a cut to make sure that your cut heals well, okay? And the third guideline is that common names are sometimes used for convenience. So case in point, we never call water dihydrogen monoxide, really never. We always just call it water, okay? So what is the name of the compound with the formula CBr4? All right, so you can look them up on the periodic table, but Br is bromine. All right, that's the element bromine. So then what do we have here? All right, do you have your guess, or your knowledgeable guess? It is carbon tetrabromide, right? It's ide because the bromine comes second because it's the higher group. In other words, it's further right on the periodic table. Carbon comes first because it's on the left in the periodic table. Tetra because there are 4 of the bromines. Okay, good. Carbon tetrabromide. Well, that's it. Like I said, it's a very introductory chapter. We'll certainly be talking more about chemistry in the chapters to come. Thank you so much for watching.